Rust in AI Masterclass by Edgar Milvis Volume 1, Chapter 3. Moving on to Chapter 3, Vec T versus ndarray strategies for multidimensional data. Moving on to theoretical foundations. Imagine you are an architect designing a library. The books are your data. The shelves are your memory. How you arrange these books on the shelves determines how quickly a librarian, the CPU, can retrieve them. This is the fundamental problem of multidimensional data in computer systems, mapping the abstract concept of a matrix or tensor onto the linear, one-dimensional address space of physical RAM. In systems programming, memory is a flat expanse of bytes, addressed sequentially. There is no native concept of a row or a column in the hardware. To represent a 2D grid, we must flatten it. The two dominant strategies for this flattening are row major and column major ordering. Now, let's explore row major versus column major, the library analogy. Row major order, used by C, C++, Rust, and Python's NumPy by default, is like arranging books on a shelf from left to right, then stacking the next shelf directly below the previous one. Analogy: you have a bookshelf with 3 rows, levels, and 4 columns, slots. You fill the top row with books 1, 2, 3, 4. Then you move to the second row and fill it with books 5, 6, 7, 8. Finally, the third row gets books 9, 10, 11, 12. Memory layout: the memory addresses look like this: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Why it matters: if you want to read the entire first row, the CPU can fetch a cache line, a small, fast buffer of memory, typically 64 bytes, and get several contiguous elements at once. This is incredibly efficient due to spatial locality. However, if you want to read the first column, you have to jump across the width of the row, for elements, to get to the next element in that column. This is a stride access, which is less cache-friendly. Column major order, used by Fortran, MATLAB, and R, is the reverse: you fill the first column from top to bottom, then the next column, and so on. Analogy: you fill the top left slot with book 1. Then you go directly below it to the second row, first column, and place book 2. You continue down the column until it's full, then you move to the top of the second column and repeat. Memory layout: the memory addresses look like this: 1, 5, 9, 2, 6, 10, 3, 7, 11, 4, 8, 12. Why it matters: now, reading a column is contiguous and cache-friendly. Reading a row requires striding. The choice of layout is not arbitrary, it has profound implications for performance. A loop that iterates sequentially through memory can be orders of magnitude faster than one that jumps around, because the CPU's prefetcher and cache hierarchy are optimized for predictable, linear access patterns. Now, let's explore the strided array pattern, the universal abstraction. To handle arbitrary shapes and layouts, we need a generalized pattern. This is the strided array. It is the conceptual bridge between a raw Vec T and a high-level ndarray. A strided array is defined by 3 core components: 1. Data pointer, a raw pointer to the start of the contiguous block of memory, the data buffer. 2. Shape, a description of the dimensions, e.g., a 2 by 3 matrix has a shape of 2, 3. 3. Strides, a description of how many bytes to step in memory to move one element along each dimension. Let's visualize this with a 2 by 3 matrix in row major order: 1, 2, 3, 4, 5, 6, shape, 2, 3, 2 rows, 3 columns, data, 1, 2, 3, 4, 5, 6, contiguous in memory. Strides, to move along the columns, dimension 1, we step by one element. The byte stride is one size of I32 equals 4 bytes. To move along the rows, dimension 0, we step over an entire row. The byte stride is 3 size of I32 equals 12 bytes. Strides array, 12, 4, the address of an element at index, row, call, is calculated as base_pointer plus row stride_row plus call stride_call. This pattern is incredibly powerful. It allows us to create views of data without copying. A transpose operation, for example, simply swaps the shape and strides. A slice is just a new base pointer and adjusted shape/strides. This is the essence of zero-copy data manipulation. A slice in systems AI with Rust is a lightweight, zero-copy view into existing data, represented by a new base pointer and adjusted shape/strides for efficient manipulation. Moving on to Vec T versus ndarray, the architect's toolkit. Now, let's map these theoretical foundations to our 2 primary tools in Rust. Moving on to Vec T, the raw land plot. A Vec T is a contiguous, heap-allocated buffer of TS. It is the simplest, most direct representation of a flat list of data. It is the raw land plot. What it is: a Vec T provides a pointer to the start of the memory, a length, number of elements, and a capacity. It guarantees that elements 0 len are contiguous in memory. What it is not, a Vec T has no inherent knowledge of multidimensionality. A Vec T is a jagged array or an array of arrays. Crucially, it is not a matrix. Each inner Vec T is a separate heap allocation. The data is scattered across memory, destroying cache locality for row-wise operations and making column-wise operations a nightmare. This is the array of pointers pattern, which is generally disastrous for numerical computing. The manual approach: to represent a 2D matrix with a single Vec T, you must manually enforce the strided array pattern. You store the data in a flat Vec T and track the dimensions, rows, calls, yourself. All indexing becomes manual arithmetic, data, row calls plus call. This is efficient but error-prone. It's like being given a plot of land and a blueprint, but you have to measure out every foundation line yourself. Systems programming analogy: think of Vec T as a raw file on disk. It's just a stream of bytes. You, the programmer, are responsible for knowing that bytes 0 to 1023 represent the header, bytes 1024 to 2047 represent the first row of data, and so on. The file itself doesn't know it's a CSV or a matrix, it's just raw data. The borrow checker ensures you don't have two mutable pointers writing to the same file location simultaneously, preventing data races at the file level. Turning our attention to ndarray ArrayView T, D, the surveyed in zone city block. The ndarray crate provides a high-level abstraction over the strided array pattern. An ArrayView T, D, or a mutable array T, D, is not just the data, it's the data plus its metadata, shape and strides. What it is, an ndarray is a lightweight view that encapsulates a data pointer, a shape, and strides. It's a fat pointer for multidimensional data. It knows its own dimensionality, D, at compile time, for static arrays, or runtime, for dynamic arrays. Zero-copy transformations: this is where ndarray shines. Because it's just a view over the metadata, operations that change the structure of the data without changing the values can be nearly free. Slicing: taking a subview of the data. This just adjusts the base pointer and shape/strides. Reshaping: changing dimensions, e.g., 2x3 to 3x2. This is only possible if the new shape has the same number of elements and the memory layout is compatible, e.g., row major to row major. It's a metadata change. Transposing: swapping axes. This is a metadata change that swaps the shape and strides arrays. The underlying data buffer is untouched. Performance guarantees: ndarray can enforce memory layout. Array of zeros, 2, 3, creates a contiguous row major array. Array of zeros, 2, 3.f, creates a contiguous column major array, Fortran style. When you perform operations, ndarray can iterate over the data in the most cache-efficient order, regardless of the logical view. Systems programming analogy: ndarray is like a database view or a memory-mapped file with a schema. A database view, create view sales_by_region AS, doesn't duplicate the data. It's a stored query that presents a logical structure. When you query the view, the database engine uses the schema to efficiently navigate the underlying tables. Similarly, ndarray holds a pointer to the raw Vec TS data but overlays a rich schema, shape, strides, on top. The borrow checker's role is now more granular. It ensures you can't get a mutable array view to a slice of data while an immutable array view to the same data is still in scope. It's managing access to the zoned areas of the memory city block. Now, let's explore explicit reference to previous chapter. In Chapter 2, Lifetimes in Ownership and Data Processing, we discussed how the borrow checker acts as a compile-time resource manager, preventing use after free and data races by tracking the scope and exclusivity of references. We used the analogy of a library's lending system. A book, memory resource, can be checked out by many readers, immutable references, simultaneously, or by a single writer, mutable reference, but never both at once. This concept is directly applicable here. A Vec T is the book itself. ndarray ArrayView T, D is like a library card that grants you access to a specific chapter, slice, or a particular topic, view, of the book. The lifetime of the array view is tied to the lifetime of the Vec T it borrows from, just as a library card is invalid if the book is removed from the library. The borrow checker ensures that you cannot create a mutable array view, or writing permit, that overlaps with an existing immutable array view, a reading permit, thereby upholding the memory safety guarantees at the heart of Rust systems programming model. Moving on to basic code example. In the context of a high-performance inference server, the way we store and access model weights or input tensors directly impacts latency and throughput. A common pattern is to represent a 2D matrix, e.g., a layer in a neural network, using a flat Vec F32 with manual index arithmetic.
This approach minimizes overhead and ensures data is contiguous in memory, which is ideal for SIMD operations and cache locality.
However, it places the burden of shape management and bounds checking on the developer. We will contrast this with the ndarray crate, which provides a safe, zero-cost abstraction over strided memory views. Now, let's explore the implementation. Below is a self-contained Rust example simulating a simple matrix vector multiplication, a fundamental operation in AI inference. We will implement it twice, once using a raw vec and once using ndarray. Cargo.toml dependencies. Notice how we define the package metadata in lines 1 to 4. This is crucial for Rust's build system, Cargo, to manage dependencies and compilation. The edition 2021 ensures we use modern Rust features, which impacts compatibility and performance. If we used an older edition, we might miss out on optimizations or safety improvements. In production, this metadata helps tools like CI/CD pipelines verify builds correctly. At line 6, we specify the dependencies section, and at line 7, we add ndarray equals 0.15. This is a key architectural choice for numerical computing, as ndarray provides efficient n-dimensional array operations. We choose version 0.15 for stability and compatibility with Rust's memory safety features. If we omitted this, we'd have to implement arrays manually, leading to higher error rates and slower development. In AI contexts, this dependency enables handling large datasets without excessive memory overhead. src/main.rs. Notice the architectural choice to use a flat vec for storage. This manual index arithmetic approach gives us direct, cache-friendly memory access, which is critical for performance in large model inference. The struct definition at lines 3 to 7 encapsulates the data, rows, and columns, ensuring we control memory layout.
If we used a nested vec F32, we'd suffer from fragmented memory and poor cache locality, which would degrade performance significantly in production AI workloads. At line 12, we see the new constructor allocating memory once on the heap. This is efficient because it avoids repeated allocations during matrix operations. The vec 0.0 rows asterisk calls at line 15 initializes a contiguous block, which is essential for SIMD optimizations. If we allocated per row, we'd lose cache coherence. Remember, in AI models with billions of parameters, minimizing allocations is key to reducing latency and memory overhead. Look at line 22 where multiply is defined for neural network dense layers. This operation is computationally intensive, so we must optimize it. The assertion at line 30 ensures dimension safety, preventing runtime errors. At line 27, we pre-calculate row offsets to improve cache locality. This is a best practice because accessing memory sequentially reduces cache misses. Without this, we'd see performance drops in large-scale deployments like Kubernetes pods handling real-time inference. Observe the nested loops at lines 36 and 41. We iterate over rows and columns manually, calculating indices in row major order. This gives us fine-grained control but introduces arithmetic overhead. At line 43, IDX equals row underscore offset plus call is computed for each access. While fast, it requires the compiler to prove no aliasing exists for auto-vectorization. We could have used iterators, but manual loops allow explicit cache prefetching, which is crucial for large matrices in AI training. At line 46, we store the sum and result row, completing the multiplication. This approach scales well for batch processing but may not leverage BLAS libraries. In production, this manual implementation is portable but might underperform compared to optimized linear algebra crates. If we used a parallel iterator, we could exploit multi-core CPUs, but that adds complexity. This trade-off is common in embedded AI systems where control over memory is paramount. See lines 54 to 56 where ndarray matrix wraps ndarray array 2. This structured abstraction leverages a high-performance library, reducing boilerplate. At line 61, new uses ndarray zeros, which internally uses a flat vec similar to our manual approach but with added safety. This is better for scalability because ndarray handles strided views and memory layout automatically. If we stuck to manual indexing, we'd risk bugs in complex operations, especially when models grow to millions of parameters. At line 73, multiply uses ndarray's dot product, which is a high-level operation. This is more readable and less error-prone than manual loops. Lines 70 to 72 highlight that ndarray may use BLAS routines or auto-vectorization, offering better performance out of the box. In a real-world scenario, this means faster inference on GPUs or multi-core CPUs. Without this, we'd need to manually optimize, which is time-consuming and error-prone for AI researchers focusing on model architecture rather than low-level code. In main, lines 84 to 86 set up a model layer with 1024 inputs and 512 outputs, typical for a neural network dense layer. At line 91, we initialize the flat matrix and simulate weight loading in lines 93 to 95. This contiguous initialization ensures memory efficiency.
If weights were loaded non-sequentially, cache misses would increase, hurting performance in production inference servers. This approach is scalable for large models but requires careful memory management to avoid fragmentation. Lines 98 to 104 initialize the ndarray matrix similarly. Notice how we use rows_mut and enumerate. For safe mutation, this is idiomatic rust and reduces off-by-one errors. The functional style here contrasts with the manual loops in flat matrix, showing how abstractions improve developer productivity. In a team setting, this leads to fewer bugs and faster iteration. However, for ultra-low latency systems, the manual approach might be preferred for its predictable performance. At line 107, we create an input vector, and at line 108, we convert it to an ndarray array 1. Lines 113 to 116 benchmark the flat matrix multiplication.
Timing with STD time instant is crucial for profiling in AI deployments. The result shows the cost of manual index arithmetic.
In Kubernetes, this data helps autoscaling decisions.
If we skip timing, we'd lack insights into performance bottlenecks, making optimization guesswork.
Lines 119 to 122 benchmark the ndarray multiplication. Comparing durations reveals trade-offs. Ndarray might be faster due to BLAS, but manual control could win in specific cases. This empirical testing is vital because theoretical performance doesn't always match reality. In production, we'd run such benchmarks on target hardware to guide library choices. Without this, we might choose a suboptimal approach, increasing costs for cloud inference. Lines 125 to 131 verify results by printing the first 5 elements. This sanity check ensures logic correctness, as floating point precision can vary with optimizations. At line 129, ndarray slice method safely accesses data, demonstrating its ergonomic API. In AI, verification prevents silent errors that could corrupt model outputs. If we skip this, debugging would be harder, especially in distributed systems where logs are sparse.
This practice is essential for reliable deployments.
By scanning this code, you go on the details on leanpub.com. By scanning this code, you go on the details on amazon.com. This code bring you to the source code repo on github.com.
Thank you for your attention.
This lesson is excerpted from Volume 1, Chapter 3 of the Rust and AI Masterclass ebook series and from the volume Advanced Memory Patterns for AI. You can find all the details here, https://github.com/edgarmilvis/rustai programming series. The ebook also includes 20 chapters with diagrams, advanced examples, and 5 exercises with solutions. I look forward to seeing you in the next lesson.